Hi, hello, and welcome. We are broadcasting live from Global Council for Aerospace Defense and Deep Tech Innovation, a premier global platform decided to accelerating innovation, strategic partnerships, cross-border collaborations across aerospace, defense, space, and deep tech industries. Today, we are witnessing a profound transformation in the global strategic landscape. Breakthroughs in space technologies, autonomous systems, satellite intelligence, advanced manufacturing, quantum computing, artificial intelligence, cybersecurity, and defense innovation are redefining the future of national security, industrial competitiveness, and global economics. Yet, alongside this technological revolution comes a significant challenge. Governments, defense organizations, investors, and enterprises are navigating an increasingly complex ecosystem filled with fragmented technologies, evolving regulations, and rapidly shifting geopolitical priorities. Visionary founders or breakthroughs innovators often struggle to access the strategic partnership, institutional capital, and global market opportunities need to scale their solutions. Promoted by the Global Council for the Promotion of International Trade and supported by the global network of policymakers, defense leaders, researchers, investors, and industry experts, established to bridge the gaps and create a trusted ecosystem where innovation can move seamlessly from concept to development. We are more than a platform, we are a catalyst for collaboration, connecting governments, defense organizations, space agencies, investors, enterprises, startups, and research institutions to accelerate commercialization, strengthen sovereign capabilities, and build the technologies that will define the future. Operating across our strategic regions, including India, the Middle East, India, the Middle East, Europe, North America, Africa, and the Asia Pacific, Global Council for Aerospace, Defense, and Deep Tech Innovation. He is committed to forecasting partnerships that drive technological resilience, economic growth, and global competitiveness. Today, as part of our visionary interview series, we are exploring the ideas and innovations shaping the future of aerospace, defense, and deep tech. Please join me in welcoming our distinguished speaker, Sreekumar. Sreeja is a seasoned automotive system engineer and technology leader with more than 17 years of experience in automotive electronics, embedded systems, software validation, and program management. She currently serves as senior program manager at Daimler Truck Innovation Center, India, where she leads body controller ECU software development, and component testing for advanced truck and bus platforms. Throughout her career, Sreeja has worked closely with global teams across Germany and North America, driving complex engineering programs and ensuring seamless collaboration across international markets. Her expertise spans automotive electronics, senior integration, hardware in the loop, platforms, software validation, testing strategies, and quality assurance. A strong advocate of engineering excellence, Sreeja believes that successful technology is built not only through innovation but also through rigorous validation, early problem identification, and a relentless commitment to quality. Her leadership philosophy focuses on building high performing teams and communicate openly, take ownership, and deliver reliable solutions for real world applications. With extensive experience in automotive body electronics and intelligent control systems, Sreeja brings valuable insights into how similar technologies can be adapted to aerospace and defense applications. Sreeja, thank you for joining us today and for contributing to the future of aerospace, defense, and deep tech innovation. It's an honor to have you with us today.
Yeah, thank you, Sushma, for the kind introduction and also for inviting me to this session. I'm very happy to be part of this conversation. So, today, what I plan is to bring a very practical perspective from my automotive experience, particularly in how we develop, validate, and deliver critical safety systems. So, I believe the same principles apply to aerospace and defense as well. It's just that the stakes are a bit higher. Yeah, so I'm really looking forward to exploring those connections with you today. Yeah, good.
Yeah, sure.
All right. So the theme for today's session is this: it works, but is it ready? So it's all about building systems that can be trusted. Yeah. So We'll start with a quick introduction about me. Sushma already spoke about my background. So I have more than 17 years of experience in automotive electronics and embedded systems. So I have worked extensively across organizations in passenger cars and commercial vehicle platform industries. And on a personal note, I'm a fitness enthusiast. I like running, strength training, yoga, all those activities. So, a lot of my leadership principles are derived from my passion for fitness because I believe to build endurance, we need strong preparation, um, you know, resilience, and discipline. Yeah, so that's how I build systems and teams that deliver under pressure. On the right side, you'll see a lot of keywords. So, these are some of the areas that I have worked extensively on during my career. Yeah, it is difficult to tell my story without the quintessential V model. So, for people who do not know about this, this is a classic model that we use in automotive software development. To keep it simple, it says how we capture the customer requirements and then how it translates through different layers um, before it reaches the implementation. And then once the implementation is done, it goes through different layers of testing before we declare it as a robust system. Yeah. So just to give you a little glimpse of each of these layers, what it means by the business requirements. So here we basically collect the customer requests. Sometimes we have new regulations that would require us to build new features. So all those come in those requirement collection. Then the next stage is to translate it into system requirements, basically translating it into something that is understandable by the engineer. Then we break it down into high level design and low level design, and then it goes for the implementation. Once the implementation is ready, it goes through multiple layers of rigorous testing so that we are confident that the system that we are delivering is robust. So this right side of the V cycle is where I have pretty much spent my whole energy over the past several years. So to give you some examples, unit testing, this is where we just see whether the logic of an application works perfectly fine. Once we are confident in unit testing, we go to component testing. This is where controller is tested as a whole. For example, if I take the case of a window operation, the hardware that is involved in it is the window switch. We have the controller and the actuators, which are the real window blades that go up and down. So here we test whether on the button activation is the window moving as expected. And that's the scope of component testing. Now comes to the system integration testing. Here, the primary purpose is to see the interfaces between each of the controllers. So you can consider an example, active brake assist. So this is a feature where when there is a collision detected by the system gives acoustic and visual warnings to the driver. And if the driver is not taking an action on time, the system automatically activates the brake application and the vehicle comes to a stop. So here there is an interaction between several controllers and all of them work in tandem to give the desired output. Yeah. Finally, we have acceptance testing, which is more like how the real end customer would try the feature on a vehicle. In certain passenger car industries, there is something called a subsystem testing also. So that would come in between the component testing and the system integration testing. So you can consider component testing having one controller in scope, system integration testing having 15 to 20 controllers in scope, and the subsystem having 3 or 4 controllers in scope. Yeah, so that's pretty much how I wanted to put it for all of you. Moving on. So now that we understood the process, let's explore how do we build these resilient systems that perform well under unpredictable conditions. The first and foremost thing is to have clear requirements. Like I already spoke, we can get a new customer request, have regulatory requirements, things like that. So ensuring we have the proper documentation and the requirements are clear to the engineers to work on is very crucial, because we cannot expect output quality without the input quality. The next one is iterative approach. I briefly touched upon the different layers of testing, right? The component, the subsystem, and the system integration. All these approaches use an elaborate hardware in loop setup where we have real simulators, sensors, controllers, and actuators that work in a closed loop environment. So setting those systems and then ensuring that the systems are stable to perform validation needs a little bit of iteration. Yeah. Also, if we are doing an automated validation, making sure those scripts are regression ready is also a time consuming effort. So refining our test framework is very crucial. Then comes the coverage. So when we have complex systems, making sure each test requirement has a test platform assigned to it, it is very important, so that there are no gaps in the coverage, and every test requirement is covered. The same goes with traceability. When there is a test case written, we should be able to track it to the requirement, so that at any point, if somebody wants to know what are we testing with this test case, they should be able to do that. Now that we know the tools and the methods to do good validation, how do we make sure that we are on the right track? Yeah, if any course correction is needed or not. That's where the KPIs come into picture, the key performance indicators. Yeah, in my experience, defect slippage is the most important KPI for testing. So what it means is, if something is supposed to be found at component testing and it is missed there and it is found in the next layer, which is the system integration testing, yeah, the first and foremost thing is to do a retrospection. Why was it missed from the component layer? Yeah, and then what are the corrective actions that we can do? Maybe add a test case, make our systems more robust, things like that. Yeah. Then the last point here is avoiding test overlaps. In certain cases, the software development is done by suppliers, and sometimes supplier also does the component testing, and the OEM does the component testing. And even within the right side of the V, the same test case can be executed by component testing and the system integration testing. So identifying these test overlap and optimizing and making sure we test with the right focus is quite critical. So my testing philosophy is test as low as possible, but as high as necessary. That's how I like to put it. Yeah, not to forget the technological trends. So we are in an age of drastic transformations. So we hear AI and all those new tools, methods, and processes. So having an open mind to explore those technological trends is very important. And we also need to have the human in the loop. Yeah, we need to try out certain POCs, see the pros and cons, and then we sign up for these new practices. Yeah, until now, I was speaking about how we can improve our testing techniques and methodologies, but I do not want to discount the fact that strategic partnerships also help us a lot in these initiatives. So, breaking silos. For example, if I'm responsible for the body controller component testing, it's very important for me to know what is happening in the powertrain department or the ADAS department, so that best practices and learnings can be exchanged. The same goes with the conferences that happens within the industry, so we can learn from the best practices that is shared across the industry. Yeah. Now coming to the second aspect, in the earlier slide we explored how we can build resilient systems, but for me the most important aspect is the people behind, right? So I think that is our biggest strength, and building the right team is very crucial to build robust systems. Whenever I set up a new team, the first thing that I do is to explain the purpose to the team members. Because I feel when the purpose is clear, we do not really need to do a lot of hand holding. And, people understand the importance of milestones, and we get results on time. There is an example that I particularly recollect. So during the pandemic time, I was part of a hill commissioning team where we need to set up a lot of hardware for testing, and there is no way we can do this remotely. Yeah. So we came up with some solutions like working in shifts with extra precautions like, face masks, face shields, gloves, and all, and, try to do our work. And I must say, it was a very proud moment for us. Without any mishaps, we were able to meet our milestones on time. The next thing is the freedom to operate. Yeah, once the purpose is clear, uh, I believe we should give the teams the autonomy, to try out different things, take risks, fail fast, and learn from those failures. Yeah, there was an incident. This is quite early in my career. We were working on program benches, which was responsible for the subsystem level validation. So you can imagine it as a memory seat, which would need two, three ECUs, and then passive entry, passive start, which would need another set of two, three ECUs. So we would manually change the wiring harness for all these things into a simulator. And this was a time consuming task. Then one of the engineers came up with the idea of a multiplex system. All of us brainstorm on it, and then we were able to develop it, and it was quite successful. And then we were able to uh, reduce a lot of manual intervention there. So I believe the autonomy really helps. I already spoke about the fail fast principle. Continuous learning. Yeah, as a leader, I always try to ensure my team has the right resources to improve themselves. Be it technical courses, behavioral courses, they have the right, inputs for this continuous learning. Yeah. Feedback. As we all know, feedback is a gift. So I try to give constructive feedback to my team members regularly. At the same time, I request them to give feedback to me as well. So that way, as a team, we improve on a regular basis. Asking for help, nothing complex here. Like whenever we feel that we do not know something or we see that there is an expert in the organization, I encourage my team members to ask for help. At the same time, offer help wherever possible. And that has really helped us with the collaboration, overall learning of the team. Agility and adaptability. So this is something I have learned by observing the startup ecosystem. We see that they are very open to new trends. They try things very quickly, and then if they want, they would do a course correction also very quickly. So that agility and adaptability is something which the legacy organizations can learn from this startup ecosystem. Yeah. So I believe these are some of the most important aspects for building resilient teams, but there are also a lot of other principles that I live by every day in my day to day. Yeah, with that, I come to the summary slide. So to keep it brief, we saw how purpose-driven empowered teams are the key to success. And once the team is established, we need to provide them with the right inputs and the iterative approach to improve the outputs. At the same time, have meaningful KPIs and collaboration to see how we are progressing towards our goals. And with collaboration, I believe that we can achieve a lot. So with that, I would like to conclude my presentation, but I would like to give a message to all of you who are listening. Yeah, with strong engineering practices are supported by dependable teams, we create systems that can be trusted even under unpredictable conditions. So that's how I see it. And I believe the same applies to aerospace and defense as well. Over to you, Sushma, if you have
Yes.
any questions for me.
Yes, first of all, thank you, Sreeja, for that insightful and inspiring presentation. So, your perspective on your work and your experience things. So, thank you so much. And then moving to my questions, my first question is, with more than 17 years of experience in your automotive system engineering, software validation, and electric control systems, how do you see intelligent sensors, embedded softwares, and advanced control systems transforming aerospace, defense, and next generation mobility over the next decade?
Yeah, that's a good question. Yeah, you spoke about aerospace and defense, but I would like to look at it from my automotive background, and I believe, the same applies to aerospace and defense as well. So, when I look back at my career, when I started, a particular function would be pretty much contained to one controller. Yeah, you have a sensor, the input goes to the controller and it actuates the actuator and it ends there. But over the years, I have seen that, functions are becoming more and more complex. Functions take a lot of sensor inputs to process and activate a feature. So that is one big change that I'm seeing. For example, if we take a temperature sensor or, pressure sensor or, the camera and radar inputs, now they are all part of a very complex decision-making ecosystem. Yeah, so sensor fusion is something that I'm really seeing these days. Another thing is, you would have heard about, software defined vehicles and software defined architectures. So a lot of complex computing is currently getting consolidated in high performance computers. And this is also, a big technology shift that I am seeing. Yeah, so to give you a brief one-liner, from a network of interconnected controllers to a very intelligent software defined architecture. So that's how I'm seeing the transition in the upcoming years.
Thank you for sharing those wonderful insights, Sreeja. So, moving to our next question. You have extensive experience in hardware in the loop platforms and testing strategies and system validation. What are the biggest challenges organizations face when validating mission critical systems? How can they ensure reliability in real world aerospace or deep technology environments?
Yep. Yeah, I think that's very much in sync with whatever I presented. I also spoke extensively about validation techniques and challenges. So I see that there are three aspects to it, roughly. The first thing is, making sure everything works in an interconnected setup. Yeah, that is what I observed even when I was designing the hill systems. So making one controller work in isolation is a comparatively easy task. But then when we have 15 to 20 controllers, the problems are some things which we do not even predict. For example, there will be timing issues, there will be communication issues, there will be network issues. So thinking of those corner cases and making sure the feature works in a complex interconnected system is very important. Yeah. Secondly, I spoke about the layered approach for validation, right? Why do we need that is basically, let's say we can test everything in a vehicle, but there are several scenarios which is very unsafe to test in a vehicle or very complex or impossible to test in a vehicle. That's when, hardware in loop systems at system integration level comes into picture. For example, creating a fault in a fuel injector of a vehicle. It's very easy to do it in a hardware in loop system, but very difficult to do in a real time environment. Yeah. Then I also see that there is a lot of virtual controller validation techniques emerging these days. Because back in during the COVID, we had a lot of chip shortage. And there were times when I have placed orders for certain controllers and they did not arrive on time. And that will affect our milestones and timelines. So having these virtual simulation environments help us to do validation when we do not have the actual controller, and also early validation, when suppliers are building these controllers, even before they are ready with the actual hardware out, we could already do it on a virtual environment. So early validation is very much possible with these techniques. So these are, some of the problems and how we can, try to address those problems. And the third thing is coverage. That's what I heavily spoke in my V model slide. When we have a complex system, there is a big chance that we will miss some things. So, making sure every test requirement is covered in either one of the platforms possible is the key to making sure the systems are robust. Yeah, so that's how I see the challenges and how you can address those. And I believe aerospace would also follow similar processes. If not, the applications would be definitely different, but I think we can do a lot of synergies with aerospace and defense and try to see how we can incorporate these practices there.
Thank you, Sreeja, for highlighting those important challenges. Building reliable mission critical systems requires rigorous testing, continuous validation, and safety frameworks to ensure performance in complex real world environments. So let's move to our next question. Having worked closely with teams across Germany, North America, and India, what opportunities do you see for collaborations between governments, industry, academia, and startups in accelerating innovation across deep tech and intelligent transportation systems?
Yeah, that's a very, very interesting question because when I spoke about the business requirements, I spoke about, how regulations drive how we design features. Yeah, so I would say government gives us the strategic direction, which we need for, implementing certain features. Then you spoke about academia. So even now we do a lot of joint collaborations with reputed organizations, colleges, where we do joint research on edge technologies. Yeah, then you spoke about the startups. Yeah, I already touched upon, we can learn the agility and adaptability from the startups. We can try out things quickly. Yeah, there is a lot of process overhead there. So I think that's really good. And then coming to the industries, yeah, the industries bring legacy, yeah, and also scale, how to scale the production, all those valuable experience lies with industry. So I believe all of these entities coming together, will help us to collaborate better, faster, have faster innovations, and also reduce the time to deployment. So that's how I see it. Definitely we should do it, yes, more and more.
That's very interesting perspective. Collaboration will play a crucial role in accelerating innovation and fostering knowledge exchange and bringing breakthroughs technologies to market more efficiently. So it's very interesting to see it. So let's move to our next question. Looking ahead over the next decade, how do you see advancements in artificial intelligence and autonomous systems, advanced sensors, and software defined architectures transforming global defense or deep tech and commercial transportations ecosystem?
Yeah. Right. I mean, yes, AI question is mandatory in this age. Yeah, we are seeing artificial intelligence all around us. And we are also in the age of rapid transformation. Yeah, I would say. So if I take the relevance of AI in validation, in my line of work, uh, earlier we used to write scripts manually and then run it in an automated manner. That's how testing used to happen. Now with llms in place, we can really feed requirements to these large language models and get automatically the test case generated out of it. Yeah, so that improves a lot of efficiency. But one disclaimer, we shouldn't forget the human in loop. There are corner cases where the requirements are incomplete, and also we need somebody with experience to really verify those test cases and make sure that it is in the right direction. So yes, human in loop along with AI can really fast track our processes. Now the second part of your question was about the software defined vehicles, like I briefly touched upon in my first answer. Yes, earlier we had a lot of distributed controllers, and when the complexity increased, our industry came up with software-defined architecture, where there is the core logic resides in the high-performance computer, and then we have these zonal uh, controllers that would take care of the sensors and actuators in that area. So a lot of thought has been put in in deriving these concepts and architectures, one main advantage is like, how it reduces the wiring harness length, then how easy it is to have over-the-air updates, and how it provides, features on a subscription basis, and also reducing the feature development life cycle. So I believe over the couple of years, we are going to see rapid transformation, and I believe, we are going to see really, big changes. And I hope that, aerospace and the automotive domain can have more and more synergies, and, we can benefit from each other's learnings.
Yeah, those are truly forward-looking insights. So the future of aerospace and transportation will be shaped by organizations. Before we conclude, I'd like to ask one final question.
Mhm.
The Global Council for Aerospace Defense and Deep Tech Innovation aims to build a trusted ecosystem connecting like investors, governments, innovators, researchers, and technology leaders worldwide. Based on your experience, what role can initiatives like Global Council for Aerospace Defense and Deep Tech Innovation play in accelerating innovation, strengthening cross-industry collaboration, and enabling the transfer of automotive technologies into aerospace and defense applications?
Yeah, I mean, it's a big role that GCADI is doing, because, firstly, you guys gave me the opportunity to come to your platform and, explain my story, how I see the automotive world is evolving. So that itself shows the commitment of this community, to go beyond aerospace and defense, and also explore what is happening in the industry as a whole. So essentially, what I feel the community is doing is um, avoiding reinventing the solution. Yeah. So I believe when we collaborate, with cross industry collaboration happens, there are a lot of, engineering solutions that can be shared and adapted across. Just to give a brief parallel from my work experience, like when we have a real technical problem, what we do is we have the people from the supplier, the OEM side, the tool vendors, as well as the engineering teams coming together and, trying to solve that problem. And most of the cases, when all these parties are together, we solve the solution quicker. Yeah, I see the same parallels, the collaboration between automotive and aerospace, and I hope, more and more synergies happen in the coming years, and together we set new standards for quality, safety, and innovation. Yeah, that's my hope.
Yeah, thank you. Thank you for that valuable insights. I think that gives our audience a lot to reflect on. What an insightful and inspiring conversation, Sreeja. Thank you for sharing your expertise and vision with the GCADI community. So, your experience in automotive electronics and software validation and collaborative leaderships. So, thank you so much for joining us today. On behalf of the entire Global Council for Aerospace, Defense, and Deep Tech Innovation community, thank you once again for joining us today. We look forward to witnessing your journey and its contribution to shaping the future of aerospace, defense, and deep tech innovation. Thank you for joining us today. Until next time, keep innovative, keep collaborating, and together, let's build a stronger, more secure, and technological advanced future. Thank you, Sreeja, for joining us today.
Thank you so much. Thank
Yeah,
you.
yeah, have a great day.
You too. Bye bye.